welcome everybody to Forever Green Fridays. Want to start by acknowledging our lovely funders, ENRTF, Minnesota Department of Agriculture, Clean Water Land Legacy, Ignite Foundation, and Builders Initiative, among many other generous funders of Forever Green that make this work possible. Thank you. I want to remind folks that we are on video, so if you're on camera, you can mute yourself if you don't want to be recorded. And if not, if you are in the room, the folks that I'm looking at, if you have a problem, let us know. We'll blur your face out. Okay, we've got Bo Hu and Licheng, Liu, and they're going to talk. But first, Mitch, do you have any announcements?
Not too major. I mean, many people are probably aware that the Canvas, formerly known as the Tri-Societies Conference, is happening this weekend, starting Sunday in Salt Lake City. And I get to give a talk that is really going to be telling the story of Forever Green. So it's the Tuesday morning Agronomy Society lectureship, like the breakfast time lectureship. Talk's definitely not done. But something will happen between now and Tuesday morning, and I'll be ready. So yeah, that's the one announcement that I had in mind. I don't know if anybody else wants to share anything else.
I mean, I could share, I'm chair of the Perennial Greens community this year, so yeah, we'll have poster and oral sessions as well. So none of them will be online, I think, but yeah, it will be good representation from the University of Minnesota, I think. For your talk, like that's what plans are.
Finally, a flight with no kids. The other thing is that our Perennial Grains reader position is posted. So that's really exciting. I'll be putting that up. I'm also giving a talk in a CSSA symposium, so I'll be spreading the word in that group, which I think is kind of a target audience. And
send me we have tons of reading talks on the Perennial Grains, so send me a flyer and I will post it at the beginning. Well, actually, our very first talk got canceled because it was USDA talk. So I'll have time to make announcements and things like that.
Yeah.
I might do some.
Okay.
I'll do some other fun things with the audience, but yeah, I will have time to make announcements like that as well.
Okay, yeah. Great.
Yeah, if anyone else has announcements for the broader, yeah, that would go for everyone.
I'll find that link and put it on the Zoom for people who are out there.
And I'll just say for any of the PIs that have submitted a proposal for Forever Green, your responses to, if you're a system science or a seed person, your responses are due to me by either the end of the day today.
But not seed, right?
I'm sorry, yes, system science. Oof, yeah. Not seed. Crop and system science. Sorry. Moving pieces. All right. Bo, do you want to start?
Okay, good afternoon, everybody. So today I'm going to show some of the recent research we have been working with the oilseeds meal fermentation. So this time it's already the end of this project cycle. So we focused pretty much on the scale up and its economic analysis for the feasibility study. So I'm going to cover mainly on the process optimization and the scale up. So this time we focus on the meal we received from Cargill about the pennycress meal. And then briefly talk about the techno-economic analysis and then the ongoing and the future work for this research. So a little bit background here is we pretty much focus on the oilseeds meal fermentation. The reason is this oilseeds meal has a high concentration of glucosinolate and other anti-nutritional factors, and also high concentration of lignose on the fiber. So we want to see whether we can ferment the meal to improve its nutritional value. In our previous study, we found that within 3 or 4 days of fermentation for the pennycress, over 95% of the glucosinate has been degraded. So this time we want to to answer some of the questions from our stakeholders, they were concerned about the cost, and especially if we have to go through the autoclave to start the fermentation. So we are trying to optimize the autoclave process, sterilization process, in order to minimize the cost. So we tried the different type of sterilization methods. So obviously, without sterilization, the fungi just didn't grow really well. So we tried to minimize the amount of sterilization time. And then we realized at 121 degrees C for 5 minutes, so this will be really quick autoclave that will be able to work best for the fungal fermentation. So we use this Asperis aureae, which is a very common strain for soy sauce fermentation. Now we move to the scale-up study. So we are using a 1 kilogram bag. So this is a bag that has which has a little bit of air permeability, so the air can filter through. And also, each bag can hold up to a little bit over 2 pounds of the material. So if you can see with 3 days of fermentation or 5 days of fermentation, the fungi has already been of 10 days. So in all the cases, fungi have been growing on the meal really well. And if we look at the amino acid concentrations and the total amino acid content in the final meal, we feel that the 3 days is good enough, it's sufficient. And if it's a longer fermentation days, we're going to see the decrease the overall final amino acid, because the fungi start to utilize some of the proteins for their own survival. So that's actually not good for the yield of the eventual feed production. So we try to we look at the inoculation age, and we found that for 4 days of the seed preparation, that's good enough.
Well, I don't
Yes.
understand inoculum age. So you age
Oh.
it before you apply it to the meal, or?
So in order to start the fermentation, we need to have the meal, have the optimum moisture content, and then we want to provide baby seeds. And this seed is mostly like fungi seed. So in order to prepare seed, we want to see how many days of a seed fermentation is sufficient.
I see.
So sometimes, if you have a really short activation period, the seeds are not very active yet, but you don't want to have the seed fermentation too long.
Yeah, okay, thanks.
So with this condition, we see that for the seed inoculation preparation, 4 days age probably be sufficient. And then for the pennycress meal fermentation, 3 days would be sufficient. And then we compare with some of the common fermented meals, like fermented soybean meal, fermented canola meal, and then our fermented pennycress meal and fermented camelina meal. So pennycress and the camelina are new crops, so these are not very common on the market. But the fermented soybean meal is a commercial product, and several companies are selling this product for young pigs. The price is around $800 per ton. Fermented canola meal is not a commercial product in the US, but it's available in other countries. And you can see that for the camelina meal and the soybean meal, with the fermentation, we actually even see the amino acid concentration increase a little bit. And for the total amino acid content, with the camelina and the soybean meal, it doesn't decrease a lot, so it almost maintains the original amino acid content. if you look at all the essential amino acids, so we say that for most of the animal feed, the dictating factors are actually the essential amino acids. So we normally have to overdose we have to overdose the proteins in order to meet the essential amino acid content. But if you look at the threonine, methionine, and the lysine, for some are good, some are not good. So I want to give you an example specific for the pennycress meal. For the camelina meal. So threonine increased significantly, methionine and lysine all increased significantly. For pennycress meal, it almost for these essential amino acids, they almost don't change. So which is still a neutral news, not good news, but not bad news.
Can I ask a quick question? Are there any of those that are especially valuable for swine? Like, are there any essential amino acids that are like the number one, number two, number three for swine?
For swine, number one is the lysine.
Nice.
Because lysine is typically the most limiting essential amino acid. But the industry is evolving. So now lysine is not that important because the amino acid itself is a commercial product now. So it is provided to the feeding
So it's
market.
additive.
Yeah, they can supplement this lysine. So then it goes to tryptophan and other threonine and methionine because these are the ones which are so expensive that typically not available to the feeding market.
Thanks.
And it looks like canola meal doesn't respond well to this at all, and a lot of these amino acids decline. Is that it?
Exactly.
Correct.
So we need to, I'll mention this one, we need to optimize the fermentation conditions to see whether we can improve some of the, using different strains or different fermentation conditions.
Did you say that there is demand for canola, or is canola meal being used in the marketplace right now?
In the US, canola meal typically is sold like $80 cheaper than soybean meal because there are several issues with the canola meal. It has still has a higher glucosinate acids. It has a higher like lignin or overall like undigestible fiber components than soybean meal. So that's why it is sold typically $80 cheaper.
$80. Thanks.
Does that mean that it can't be used? Like if it's cheaper, does it mean that it's
It mostly used in
quality?
it mostly used in the cattle or dairy ruminants, not widely used in monogastric animals. For other countries, not a very common practice in the US, but other countries, they do a fermentation to use a canola meal for the I'll briefly mention this one a little bit later. So now let's switch the gear to the techno-economic analysis. So this will be the whole fermentation process. We have the oilseed meal. We have to have the proper site for the fermentation, and then blend it with a little bit water to get a 70% of moisture level, and use a cooker to sterilize it. Bag filler to put in the fermentation bag, and then on the other side, that's back to the question about seed fermentation. So we need to prepare for the seed, and then mix it with the inoculation ratio and start the fermentation. And eventually we're going to get the fermented feed. So this will be the final condition we optimized from our scale-up study. So that this will be the cost estimation for the feedstock, for the nutrients, for the seed fermentation. And these are the capital investment for the processing equipment we find from different websites. Adding them together, so the operational cost, the capital investment, and when we put into the internal rate of return, in 10 years, we got 12% of the return. If we are selling this meal fermented meal at $270 per ton. I want to give a little bit of reference here. So the fermented soybean meal is sold around $800 per ton. For the regular soybean meal, it is sold roughly like a $350 to $400 per ton. And right now, 270, we're using very conservative number. So we are hope because our fermented pennycress meal should have a better digestibility or better nutritional profile. So this 270 number is actually a very conservative number to use. So some of the ongoing and future work, we will start to work on the mouse feeding test with Dr. Chen. And for the next, because right now we have a little bit larger amount of materials available so that we can start to feed the mice. In the future, we hope that we can feed the pigs or chicken if we have a 50-kilogram bag fermentation available. Now we have 1 kilogram, so couple kilogram will be sufficient to feed the mice. That will be answering some of the questions about chlorella meal. So we want to share, we are receiving another grant for so our chlorella fermentation originally was funded by the Norwegian Research Council. So they're interested to see whether they can use a chlorella meal to feed salmon in Norway. So they found our research to see the fermentation to improve the nutritional value. And now this is a new project USD is going to fund to see whether, overall, how to use the fungal fermentation to improve the nutritional value for the monogastric animal feed, so in the US. So back to the question from this room. You see that some of the amino acid for the fungal fermentation is not ideal. And we are proposing to use a sequential fermentation here. So the first fermentation will be the fungal fermentation, and will be followed by bacterial fermentations, most likely a silage process. So we will have fungal pretreatment of fermentation as a pretreatment to reduce the fiber, reduce the glucosinolate, synaptic acids, and the phytate, and then have the silage process to preserve the feed and to improve the palatability and to further refine the fermentation parameters. So that's all for my presentation. Now open up for any questions.
I think it's up there, but I just want to digest, with the group, the assumptions that go into it. So what scale of processing are you assuming here? Is this the 50-pound bag, or is this like a full, industrial vat scale?
We are using 50 kilograms a bag, and we are growing this is a 1,000-ton scale, and 1,000-ton we're going to use 100,000 50-kilogram bag.
Okay.
For the commercial scale, we look at what kind of fermentation bags will be available for the fungal fermentation. Normally they have the 1 kilogram bag or 50-kilogram bag.
And then for the commercial soy and commercial canola meal that's fermented, are they doing it in bags, or are they doing it in even larger scale?
That's a good question. For the commercial fermentation in the US, the commercial fermentation for soybean meal is done by the bacterial fermentation. They're using liquid fermentation and using one of the lactic acid bacteria. So the goal is a little bit different because the soybean meal, they don't have they don't have like a lignin in there. They don't have a glucosinolate there. They don't use a fungal strain. So they mostly use a lactic acid to hydrolyze the protein a little bit to increase the digestibility for young pigs. So those are the really very specialized diet, not for the grow finish pigs, just for the pigs that recently stopped from the mother's milk. They want to feed a little bit like special diet for their digestion system.
And canola meal fermentation, is that also bacterial?
Canola meal should be mostly fungal fermentation because the canola meal has a exactly similar feature as a pennycress meal or camellia meal. So very high in lignin, very high in glucosinolated salicylic acid phytate. So those are normally for the solid state fermentation. But solid, we don't, if we don't, if we it's like a done in a commercial like a company, they will use a large scale solid state fermenter. So that we can easily go to 1,000 gallons or several thousand gallons.
Right.
Here, this is where what Shauna I are imagining here is still, if we don't build anything, let's see if our farmers want to adopt this technology. How can we enable them to have like a minimum amount of capital investment so that they can do this by themselves?
I see, okay. And if it were to scale up to an industrial scale, obviously the capital expenditures up front would be much greater. But would you be able to produce at, let's say at 270 a ton? Would the profit margin also be higher at the other end because of the economies of scale, or is it actually like optimized scale to be set?
So compared to the liquid fermentation, solid state fermentation by nature is relatively smaller scale. And but compared to this one, I'll say compared to the bag fermentation, if we have a large fermenter to do the solid state fermenter to the fermentation, I will imagine that the energy cost and operational cost will be a little bit lower. So the labor cost will be a little bit lower. Because if you run industrialized equipment, you can automate a lot of stuff. Bag fermentation is still very labor intensive.
Yeah.
So this is a analysis that will look at the economic viability of putting a farm scale solid fermentation operation up.
Yeah.
You might have said this, but I think I might have just missed the numbers, but so what would that be replacing in the swine diet? Is it just like a mixed ration with a whole bunch of expensive additives? What's the motivation for a swine producer to moving in this direction and even considering this type of on-farm investment?
I probably should have our animal science team member here. So for the animal diet, the most expensive material is energy. Second one will be the proteins. Third one will be the phosphorus. So these are the three most expensive components of the animal diet. So eventually we need to formulate. So the traditional diet is corn, soybean meal.
Yeah,
that's the traditional diet. Here, what we are teaching here is, so this fermented pennycress meal or fermented camelina meal will be some sort of like a replacement or of the soybean meal. And they can use this as to mix with the corn or something to formulate the diet.
right now the corn and soybean meal diet is supplemented with amino acids and proteins and
Yeah,
it's not.
If it is a corn soybean meal diet, it's a complete diet. Soybean meal is a complete diet.
Okay.
They don't miss anything. But in the US, like 20 to 30% of the diet is actually not a soybean meal. It's DDGs, the corn silage from the ethanol industry. That specific material is short of a lysine or some essential amino acids. So if we formulate corn, soybean, a little bit of replacement with DDGs, then we need to have nutrient supplements.
Okay.
Canola meal or pennycress meal compared to DDGs, it's actually a little bit better feed in terms of amino acid profile. So if you look at the pennycress meal or camelina meal or canola meal, they're actually very similar to soybean meal. They have a very balanced nutrient amino acid profile. It's better than DDGs. But the drawback is, this one has a high concentrated lignin or glucosinolate, phytate, those kind of stuff. Yeah, I think I was brought into this group originally because of the fermentation we do. We can, I didn't show this in a, I have a, so this is a slide. You can see that with the AO fermentation, within 4 days, 95% of the glucosinolate from pennycress meal is gone. this is true for our colonial meal fermentation also. So I think what we can contribute to the breeding world here is, David has a whole lot of stuff to breed, at least removing the glucosinate, it will significantly reduce the breeding work for now. Yeah.
Cool.
But even for the colonial meal, Canadians have been doing for decades to reduce the acids, anti-nutritional factors. But still, there is a room for the fermented meal in order to be used in like a higher end or like a little bit more expensive feeding method. Yeah. Fermented meal has a lot of potential in other aspects, increase palatability, sometimes even serve as a prebiotic situation. It's not fully explored on this experiments yet.
Okay.
There was a question of what DM is, the acronym.
Dry matter, sorry.
Dry matter.
Dry matter, I'm sorry, yeah.
You're fine. Oh, and then we have another question, from Cody. Given the low prices of corn and soybean for feed, do you have an idea at what price or BU this on-farm investment makes sense?
Per bushel, Cody, let me go back to my office and I can convert the unit and I will send to you. So here, if you look at for 1,000 ton annually, the capital investment will be $253,238 for the capital investment. So if it's 1,000 ton, that'll be 2 million pounds, right? So 1,000 tons should be two. Yeah, that will be that if we can convert the bushel, that will be something that we can do a calculation.
What's the, like, in that number of tons, like what percent of the market, or like what does that mean in terms of like
Percent of the
the
market.
amount of tons that are fed to pigs every year? So,
I feel this will be endless market potential because pennycress meal or camellia meal, this is cover crop. The scale of this oilseed production, there will be nothing compared to like a soybean or canola in the global market. This compared to soybean or canola. Canola is the largest oilseed crop. Soybean is number 2. Compared to this 2, our cover crop production will be teeny tiny. Yeah. So what we are here is still, we are trying to. We want to prove that our pennycress meal, camellia meal, has a potential to be equivalent at the soybean meal, and you sometimes probably can ferment it can be better than soybean meal, so that we can put in the competitive market. Yeah, back to the recent question. I think Cody asked this question. So right now, the feeding market price is very low. There's a little bit reason behind it because because it's California legislature, US is converting 40% of the soybean oil into biodiesel or renewable diesel. So this literally put soybean meal super oversupplied domestically, and then with the current trade war, so it's hard to export all this extra amount of protein-rich meal to the global market. So that's why temporarily we have a very low feeding price, soybean meal price, domestically in the U.S. But I don't feel this is a long-term issue, because if you look at it globally, protein is always the second most expensive component in the feed. So down the road, maybe a couple of years later, global market, they will absorb all the protein products US produced, so down the road it shouldn't be an issue. But in the short term, within this few years, soybean meal price, like a couple of years ago, it was $400, $500, now it's $300. And the oil is much more expensive. It's because it's policy.
Well,
there's a lot to dig into. I need more time to get my head around all the economics, but I just want to say that it's great to have this TEA. And I think that this is the direction that we, as Forever Green, leaders and organizers want to go in to have information like this to make good decisions about where do we continue to invest? Where do we think are the economic pathways, commercialization pathways for different crops? We've got a lot of information about what the markets are, but especially as particular end use technologies come forward like this, we need to get these hard numbers to have some sense of, what do we pursue, what do we push, what direction do we push it in? So yeah, just thank you both I mean, this is the first TEA I've seen in a Forever Green Lab meeting. I haven't seen all Forever Green Lab meetings, but I think it's kind of a new frontier, so it's cool.
It's only been here for 3 years.
Go back.
I hope everybody has seen this, and it is my first time introducing myself here. My name is Licheng Liu, currently in the BB department and leading the project trying to assessing the Kernza environmental impact through a knowledge guided machine learning project. And this is a project led by me and also Jessica and Jacob here, and also we collaborated a lot with Devin Mola in this group, and we are trying to find out how Kernza can help us in reducing the leaching and also mitigating the climate change, even though under current circumstances that we shouldn't see the climate change. So talking about the Kernza, I don't think I need to go into deep about the Kernza because most of you must know more than me. But I would like to still remind myself that Kernza is a perennial grain used for multiple uses like baked goods, pasta, beers, and also you can enjoy as a whole grain like rice. And unlike traditional annual grains, corn, soybean, Kernza thrives for multiple years without replanting. So it can reducing the tillage to the soil and also resource intensive inputs like fertilization, and its intensive root systems can go deep to 10 feet depth, preventing soil erosion, cleans water, and improve soil health. And that is basically why we put a lot of focus on the Kernza. And from our previous study, and something has been tested over a few sites experiment, like it potentially can mitigate climate change by sequester 300 to 100 pounds of CO2 per acre annually in the soil. And another thing is it can significantly reducing the fertilizer input into the soil and also significantly fix the fertilizer nitrogen inside the soil so that it can reduce 98% of the nitrogen leaching compared to the corn and 96 compared to the soybean. And also these results are based on few sites experiments. And also it can improve the soil health by providing more soil organic carbon, reducing the soil erosion, and also reducing the leaching we have mentioned before. And also because of it can start growing early in the spring, so it can providing critical shelter for different kind of animals, and so it can strengthen the wildlife habitats. But most of the results are based on the limited site studies. So that's why in this study, we want to extend this kind of assessment into the regional scale by combining the modeling power and also by combining the most advanced AI power, which we thought there is a big way using the combining the scientific knowledge with AI. We call knowledge guided machine learning. And what we are doing here is trying to developing such kind of techniques, and by combining the existing field level data and also by combining the power of the scientific understanding, AI modeling to help us inform the decisions for expanded Kernza growing. And so here is the whole workflow, and we are basically in the middle of this project. At the beginning of this project, we have I'm going to introducing what we have done so far, including the data collection and initial modeling test with some simple machine learning models, and also the process-based modelings, and also the next step in order to do the non-guided machine learning model. We have also designed a general platform trying to quickly develop any kinds of KGMLs, and which we think might be also beneficial to the whole community. And if you have a few sites of the simulation, a few experiments data, and you would like to use model, and specifically you don't want to use black box models, then that platform might be useful for you. Okay, starting from the data collection, and thanks so much for the Jake and Jessica. So help us a lot harmonizing this data set. Though there are still problems we need to deal one by one, but right now we have, after filtering and compiling, we have already get a data of 800 annual samples and across 8 sites for Kernza. And those annual samples including variables of seed yield, straw yield, heat yield, nitrate leaching from some synthetic simulations, and soil carbon and nitrogen. And also we have about 600 daily variables, including N2O flux and CO2 flux, and mostly from a few sites to support the Kernza modeling. And those are observation data we have compiled so far. And some data, and we believe this might be the current most comprehensive data set over the Minnesota. So we are going to use this data set to support our next modeling works. And some preliminary data analysis, and it's like at plot level and both side level, we have found that the straw yield, seed yield has a strong positive correlation, while nitrate can give a positive feedback to the seed yield. And while stand age, meaning the longer the Kernza stands, the less yield we can get. So this is a very general overarching data analysis based on current data. And also, next step, we have also found the trying to allocate the spatial distributions of the Kernza yield. Basically, you can see it has a trend that the west, close to the west, we're going to have a higher yield, and also northern part has a higher yield than the southern part. So that is only analysis based on these 8 sites, and we don't know whether we extrapolate to the regional scale, this pattern can still exist. But from these 8 sites, we can see this clear pattern that on the northern western side, it's higher, and the southern eastern side is lower. And also, we based on this pure data analysis, then we have also using machine learning model to do some further analysis. And by running a machine learning model, we need drivers. We have collected drivers. We're trying to use the drivers mainly from the observations, but if we are we need some extra drivers or have some missing drivers from the metrology code information, soil information, or management information. Or management information we cannot compensate from any other data set, but metrology data, soil data, if we have some missings, we are going to use NLDAS which is the reanalysis data. We are going to use to fill the gaps. So and also we have soil data. If soil data is missing, we are also going to use G-Circle, which is also a reanalysis data pool, to compensate the missing data. And then some preliminary results is if we randomly split the training data, testing data for any kind of modeling work, we need to split the training and testing, meaning we use the training data to train the model or calibrate the model. We're using testing data to which is has not been seen in the training data to test the model performance. All the results later on is test results over those testing data, which has not been seen by the model. And this is a data this is the results based on the annual observations and the randomly split the data into training and testing set. And we can see that if we only consider the variation and randomly and split the data, we can capture most of the variations, and our model can fit pretty well and to predict the seed yield and straw yield. And but that is not the end, because eventually we want to extrapolate this model in space and time. So we want more about the extrapolation power in space and time. So the more okay.
Just as a really short, is this the machine learning model or
Yeah,
is this
this is
the
the
process
machine
model?
learning model. Process-based model has not been introduced yet.
Okay.
So this is machine learning model results, pure machine learning model results, random forest, and we just use them to do some simple data-based analysis and try to extend our ideas how far we can go from current data, from current observation data.
And this is the relationship between the training and the predicted, or like predicted and actual,
Yeah.
I mean?
The true value is the x-axis, the value is predicted value. And the left side is seed yield, the right side is straw yield. And those two variables were chosen currently because they are most abundant variables in our annual data. And random split is perfect. And by this random split, we can also do some analysis like you may hard to see, but we can do some feature importance analysis and also feature combination analysis. And what we have found is the soil organic carbon and plays the number one role in explaining the variation between the different sites and also the maybe across the different year. So that is the SOC. And also the nitrogen fertilizer is the second role. Right after that is precipitation and radiation and the stand age. So those variables are very important in explaining the variation of the data of the seed yield and straw yield. And while right side is like performance when we try to using different combinations of the input, like Kernza itself representing, we only using the Kernza observation data like nitrogen fertilizer stands the seed yield and straw yield. And we can also have the meteorology data from the real analysis data and soil data from real analysis data. We have those data being added into the modeling, and we have found that in most of the cases, meteorology data can help improve the performance, and while improve the model's ability to explain the variation, while as adding soil data basically have no meaning to the model. So that may be due to the in most of cases we didn't have a very comprehensive soil data and as we expected. So some of them has been filled by the reanalysis data. So they are not very matching with our sites. That might be one reason. Another reason might be the soil data. We have very few sites. So if we want the model to learn the variations across the site, it's going to be very difficult. I'm going to show that later. Because as I have mentioned, this is not our final goal, just analysis, but we want to see from this data how far we can go for the regional extrapolation and the temporal extrapolation, like predicting the unseen time and unseen locations. The first is a temporal extrapolation. This is going to be interesting. Like we have like 9 years of data, and this is 9 years or 10 years, 9 years of data from 2012 to 2021. And we use the 2012 to 2017 to train the model, and using the rest of the data to test. This is we use this data like a few years before to train the data, and the rest of 3 or 2 years to test the data. And what we have found is basically you can see the significant reduction of the performance, and especially you can first see only with Kernza data in the third column, and we can only reach about 0.3 meaning our design model based on historical data can only explain about 30% of variation in the future. And also our meteorology data and soil data individually, when added into the model, it can hurt the performance. It means this data, because they are reanalysis data, not has a good match with the observations. Using them to drive your model in the future will hurt your performance. It's not a good practice by adding new data. So it means that our data itself, annual data itself, right now may not be very robust in temporal extrapolation in the future. And for spatial extrapolation, here we didn't show training the performance. We only show the test performance for seed yield, straw yield, spatial performance. All of them are negative, so I didn't show them yet. And here is a seed yield prediction, spatial extrapolation, meaning for those 8 sites, we use like 6 locations. We use a cross validation, 6 locations to train the model, and 2 locations as a testing site. And there are because we have a rotation, so in total like 28 experimental combinations has been conducted. And we have calculated the mean values of this experiment, and we have found that all of them reduce a lot from the random split, the performance. You can see it means when you extrapolate from the training in the 6 side and extrapolate to the other 2, you can only expand like less than 30% of the variation. And it means your model are not robust to extrapolate in space as well, if we only rely on the observation data. So the observation data is itself, even though I have said it's the most comprehensive data in Minnesota, it can only do this job if we only using observation data. And that's why I also want to say that that is a previous analysis. And another thing is limited data in the real world, as I have mentioned, has well prohibited the effectiveness of machine learning model, especially when extrapolating space and time. The right figure is basically the missing value amount in our data set. And we in total have around 800 samples. But we only have seed yield and straw yield in most of the samples, but other variables are basically most of them are missing. So in order to define develop a model can assess not only the seed yield but also the environmental impact, including the greenhouse gas emissions, including the soil health, soil and carbon changes, leaching, and we might need to find other data sources. So that's why we move into another, we want to combine another data direction, and which is a process-based model, generated synthetic data. Process-based model is basically a kind of model designed based on the scientific understandings, and the model we are relying on is called Environmental Policy Integrated Climate Model, EPIC model. This EPIC model previously first designed by the Texas A&M University, and this model has was used to forecast the Kernza both from biomass grain yield, alpha biomass, and the corn soybean yield impacts on the different nitrogen rate and the cropping rotations. And this model has incorporated these processes inside it, so that it can have some constraints in the space and the temporal extrapolation. And right now, the model also has been evaluated the crop productivity versus impacts on the population of the water below the rooting zones and greenhouse gas emission and natural leaching losses. So we believe this model is right now it's a perfect fit for our project to preparing those synthetic data. And the David Mola and his research scientist Mohammed are helping us right now preparing this data. And the Win Epic version 6, which is also the most recent Epic model right now, is currently being used to generate the data. And here is our generations, like the crop rotations and all scenarios, we use the epic model going to generate. We designed the 4 different kinds of scenarios, trying to include the different kinds of rotations, and including the Kernza alpha Kernza, and also Kernza corns, soybean, corn, soybean. Every Kernza going to be planted 3 years right after, like combining with other crops like alpha or corn, soybean, soybean, corn, soybean. So that is a different kind of combination, and each crop rotation, this kind of crop rotation will be repeated 3 times, and in total 18 years simulation will be run for a single scenarios at a single site. And we are going to run this over. Previously, I have shown a map. We are not going to only run over those 8 sites. We are going to using these 8 sites to calibrate the model and assimilate over 20 the agroeconomic region. Every region we are going to sample about 10 points, so that we in total going to have about 20 sites of those simulations, and that's going to be a huge amount of data. And not only the annual data can be provided by the EPIC model, but daily simulations of the N12 fluxes and also other variables like Licheng can be generated by the EPIC model. And currently we have already got the annual data, and this is an example of the annual data. We are currently trying to work on the annual data combining with real world data, so that this data can be used as a one way to constrain our model and pre-train the model. And also the model itself can the structure and the equation it used can be used as a scientific knowledge to constrain the simulations. So that is basically what we have done for the for this project using the data and synthetic data right now. After that, I'm going to introducing how exactly these all those pieces can link to each other so that we can move forward, and by the knowledge guided machine learning model. So a little bit introduction to the knowledge guided machine learning model is we all know that modeling is a way we measure or predict phenomena that are difficult or impossible to measure directly. So that that's why we're using synthetic data generating so many those process-based models generating so many synthetic data to compensate our real-world data. And this is a 2-dimension coordinates I'm going to use to explain the different kinds of models comparing with field experiments. Unfortunately, field experiments is on the left bottom corner because we all know that even though they are very precious and labor intensive to collect them at a single site, they can provide a little amount of data, and basically with those small amount of data, they can provide a little amount of scientific knowledge. We need a accumulation of those data to eventually get some scientific knowledge. And based on this data, we have different kinds of modeling approaches, like process-based model I have introduced before. Here is a more general definition of the process-based model. It is a numerical representation of one or several processes, characterizing the functioning of complex systems. And they basically designed based on scientific understanding, so it is a glass box. And one example here is this is one representation in the model trying to simulating the substrate concentration like methane, ammonium concentrations inside the soil, and it considers the fluxes, the transport, oxidation, and production. And one full process-based model can have dozens of those processes and hundreds of parameters and over 1 million lines of code. So that is basically how complex the process-based model is going to be. So that's why I summarized the pros and cons in the below table. And the process-based model with its alone, it can reach high interpretability because it's glass box. It don't need that much data to calibrate the model, but it normally can only reach medium accuracy, and its efficiency can be low because of high complexity. and also the structure data flexibility is low. Any kind of new data or new knowledge added into the model need heavily rewriting of the model. And another side is the machine learning model has been, maybe you have heard so many times in the recent 2 years because of the GPT suddenly comes out and blow our mind. But what is the basic concept of this kind of tool is a machine learning model is built on the machine learning algorithm and trained primarily based on data. And then I want to see here is a conventional black box models. What are the conventional black box models actually are basically are foundations of many current AI applications. Basically, over 90% of current AI applications are black box models, meaning they only rely on the data training, not many scientific knowledge constraint of them. And there are some different kinds of model structures like we can use the recurrent neural networks. They can consider temporal dependence. Convolutional neural network consider the spatial dependencies. And transformers, they are the foundations of the GPTs and many AI models. They considering the attention in the global context, try to give you an understanding of that. But none of their models are a glass box as process-based models. So I have summarized the pros and cons in the below. Even though they can reach high accuracy, high efficiency, and really welcome new data, new structure, but it can have really low interpretability and normally needs huge amount of data for training. And so that we can combine those two kinds of models in our work. And that comes out the hybrid AI modeling. And more specifically, in our work, we are going to design the knowledge-guided machine learning. And other terms you might also heard, like physical informed neural network, differentiable programming, they are similar to the KGML or within the KGML big umbrella. And this work, it can overcome the previous limitations like the process-based model limited by the data usage efficiency to capture the high spatial heterogeneity. And also the conventional black boxes are limited by insufficient repetitions of FOIL processes so that it is hard to be explained and need huge amount of data to train it. And while the hybrid AI models, it combine the data efficiency with mechanistic realism. And then the next question going to be, how can we achieve the hybrid AI model? And we have a one proved solution in our previous studies. Considering, I would like to use an analogy like robot learning cooking skills to introduce how we incorporate the knowledge into the AI. And imagine the black box machine learning models is just like a robot learning how to cooking a pasta by trial and error. It need to try millions of combinations of different ingredients and operations. But the truth is, our human being already have a very structured recipe. So encode this recipe into the robot while significantly reducing the trial and error times. And we call that knowledge-guided architecture. You can encode the structured recipe into the machine learning model. And another thing is we have so many well-trained human shelf. So we can let the robot observe the shelf to before starting trying by itself. So the robot may mimic the gestures, operations, and gradient combinations from the shelf, and we call knowledge-guided pre-training. And the one following of that is we can also set up some rules, let the robot knowing that there are some fundamental rules we all treat it as common knowledge, but the robot will never know, like the do not burn the food. The human will not eat burned food. And also the mass will not disappear or appear suddenly. So those general rules, the robot will not know. But if you set up these things as a common knowledge, as a common constraint to the robot, then the robot learning trajectory will be constrained to like get a very easy way toward to the better optimal global optimal. So that we in machine learning, we call that knowledge guided loss function. So with these three kinds of ways, we can incorporate the knowledge into the AI. And then I would like to introducing a little bit more on this project. How are we going to do that? Is basically we are going to combine the EPIC model simulated data with GRU model and to design a digital replica of the real world, a real Kernza's growing environment. And we are trying to capture the carbon cycle, nutrient cycle, thermal cycle, and hydraulic cycle, eventually going to simulate, provide output of CO2 N2O yield, leaching, and also the discharge flow, so that we can have a better sense of the how the Kernza are going to influence the environment. And we have every basically every term has a previous example, successful example we can directly borrow for. So this project is going to follow this pipeline and design this kind of hierarchy GRU guided by the knowledge. And in order to better design this KGML, we know that KGML is also a very good idea, maybe from our previous experience, but we also found it's very challenging to design an effective KGML because it requires deep understanding in both domain science and deep learning. So we like previously for KGML models, we need over 1,000 lines of Python coding and dozens of hyperparameters choices. So in order to reduce these efforts, we designed a library called Python KGML. And this Python KGML design in this project is trying to reducing the efforts and also can be reusable for other projects. And this previously we used 1,000 lines in Python, and currently we have already released this package. I'm going to show you in the later slide, and this can reducing this effort into 100 lines with just call some predefined functions or configuration terms. And right now we are working on is trying to combine this platform with the AI interfaces like GPT, so that more user-friendly designing of the KGML can happen, even you don't have like programming knowledge. And currently, this is the current phase of the Python KGML, and Python KGML version 2 is currently released, and it has already encoded the benchmark data sets and the model selection, training, testing, and pre-training. And the pre-training processes, loss function design, model structure design, and our targeted users are educators, students without or limited coding experiences can be used for teaching, and always also non-computer science background researchers, so that they are able to do simulations like us, combining their data with and their knowledge with AI tools, and also the stakeholders. This is something. Can be done by current version, but if we combine with a chatbot, we believe that will be the potential. And that will be all. And just to give you a glance of what is that looks like. So when you open that link, you are going to see this GitHub. And this GitHub, we already have some followers, and please help to populate to anyone you think might be able to use this. And we have a very detailed structure how to use from the beginning to the end, like including the data loading, data processing, and training, testing, loss function design, structure design. And we also have a tutorial designed here, and it can be used locally or using the Colab if you don't have a GPU on your computer. So it has everything has been demonstrated using our own benchmark data. And if you want to use your own data, you just process your data into a format that we can adapt to this model. And just a little bit recap on that, what we have done so far, and it's we try to using the knowledge guided machine learning model to assess the Kernza environmental and economic effects. And so far we have compiled Kernza observation data covering 8 sites. And the EPIC model, the process-based model, is used to generate the infect data to compensate the real-world data limitations. And also a general KGML platform is designed to support the further quick synthesis of this data process-based modeling and machine learning. So that will be everything I would like to introduce today.
So when you had the four and the kind of the XY axis of data use and scientific knowledge use, said that a KGML has data efficiency.
Yep.
So what do you mean efficiency? Because my understanding would be that we'd be feeding the model with quite a bit of data. You would just be able to generate a lot of that data in process-based modeling.
Yeah.
So it's a lot easier to generate the data than having to go run thousands of field experiments. Is that what you mean by data efficiency, or is it actually doesn't need as much data because of the way the model is?
Yeah, data efficiency can be understood in two ways. The first way is it can welcome new data very easily. And like previously, it is basically impossible, like within 2 months to get a new variable added into the process-based model. But right now, maybe we only need 1 day or 1 click for machine learning model or KGML model to add that new data. So that is leverage of the advances of machine learning model adding to the process-based model. And another side is data efficiency is because we have a process-based model generate the synthetic data, and we are going to leverage that synthetic data or that knowledge so that we don't need that much data in training a machine learning model. It means we previously, like what I have presented, only using our current collection of the real world data, how poor it can be in regional and temporal extrapolation. But later on, we might be able to significantly reduce the need of, but that maybe the machine learning model is not well trained because of limited data. And the thing is, we can leverage the synthetic data because synthetic data basically is cheap, free, comparing to the real world data, and we use them and increasing the data efficiency or using how to use the data into of the real world from the real world, so that those data can be better used. Like they can use to fine tune our model and slightly not design the relationships like between the temperature and crop yield directly, but just tune these relationships by the real world data. And by doing that, the data efficiency will be significantly improved. So those two things is like trying to combine the powers of the both sides to together increasing the better use of the data from the real world, and also the welcome any kinds of new data and from the current data accumulation, not only like the data we have, but we have a possibility to like incorporating the remote sensing data and also the many other data sources, because we are easy to incorporate them into a machine learning model structure.
Pete LaFontaine said, does CFANS have specific policies about using AI?
Yeah,
I mean, the university has contracts with 2 AI bots.
yes.
I don't know if that's an answer.
Yeah, I mean, I just went through the process of requesting access to our enterprise Gemini yesterday.
Yeah.
And there are policies around, like HIPAA type data.
Yeah.
And putting data up that is private and copyrighted, and we don't own the copyright and things like that. And then there's policies around in an educational setting, using it with instructor permission and not using it if you're not allowed to use it per the instructor and that sort of thing. But that's just what I deduced from the little form I had to fill out. I'm sure there's more infrastructure than that, but I don't think that the university is discouraging the development of AI-based research tools. So is that what you're getting at, Pete, or what are you curious about?
Yeah, I mean, I guess we heard a bit about the distinction between generative models and machine learning. I'm it's a much broader question than this particular research study, so I'm loath to open up the Pandora's box, but just curious about, particularly when it comes to machine learning, what parameters the university has set in place to ensure standardization or just a sort of overall approach to using the technology.
I don't know if this is quite what Pete is getting at either, but I have a kind of a follow-up, Licheng. Because, yeah, or how, I mean, I theoretically, I understand that how, you know, machine learning models are a form of AI, right? That's what you're training, yeah, you have a model that you're training with data.
Yeah.
But, I wonder if, I don't know quite how to say this, but I wonder if the, like, modern thinking of these, like, AI bots that are becoming really prevalent, maybe we're disentangling the fact that, like, machine learning models have been used in science for a really long time. You
Yeah.
know, like, so that might, I don't know if that helps your thinking at all, Pete, but like, the idea of a machine learning model has been around for longer than ChatGPT. As a method in science.
Right.
Yeah, that's a good point.
You know,
Yeah, and as machine learning and generative AI get more and more entangled in both research tools and also sort of commercial applications, I'm just going to be really interested to see how institutions deal with that entanglement.
Machine learning for AI, for science, or AI for science in recent few years has been mentioned a lot, and but machine learning for science has a long history. But actually, machine learning is a subset of the AI, and what I have mentioned is also more related to the machine learning, not directly using those generative AI tools in the study. So that will be the first the biggest differences. And another thing is comparing the previous like uh, machine learning for science and to the current what we call AI for science. The main difference is the transaction between the shallow neural networks to the deep learning neural networks. And the shallow neural networks, maybe tree-based neural networks, they can be deep, but normally we call that tree-based neural network or shallow neural networks, or something you might be able to explain in the middle, and like some machine learning things, to some deep learnings, neural-based deep learning frameworks, so that you will never know what happens inside. So previously, like tree-based model, as long at least you can explain to some extent of the feature importance or something. But right now, deep learning models, you can't tell from the beginning to the end how it do the mapping. And so that's why the current, if you want to have the more robust powers of the predictive power, you might lose some interpretability. But right now is the predict power increasing a lot, but the interpretability didn't follow the lead. So what we are trying to do is we trying to let the interpretability increasing along with the predictive power as well. So that's why the hybrid AI model has been called a lot in the recent few years. And AI for science also been there is several NSF call like AI for science call. So the starting from 2023 to current, there are several calls for this kind of revolution, and they are not specifically related to the how the generative AI being used, but the more specifically like referring to the specific design, the models for solving scientific questions in different kinds of science domains. But GPTs and also many other kinds of generative AI models, they are not be able to do that. Because the thing, if you have tried GPT, the very vivid example is when you try to upload a small set of the data from yourself, and it already takes a super long time for them to do the analysis, because they are basically designed from the languages, and the main training data is languages. They are not designed for science. And some models have recently been designed for the foundation models. They also call the AI foundation models, and they designed based on the satellite imageries. But they are the revolutions of using AI in computer visions. But the true innovations we want, like for those analysis of the different carbon nutrient cycles, ecosystem services, and also many other things, we cannot find a reliable application from the predefined AI tools. So that's our goal.
Speaking of applications.
Yeah.
We have a question online from Catherine Chute. How do you anticipate this model will help Kernza growers or buyers? Will it help predict yields per acre and therefore total volume available?
Yeah, this is a really good question. Our event, let me go back to the previous this slides. It's going to be very straightforward explaining what we want to do eventually. So we can, based on this data combination synthesis work, we are going to have a robust model can do the temporal extrapolation and spatial extrapolation, simulating over a relatively long period of time over whole Minnesota to assess where we can have the maybe better yield of the Kernza, where we can have a better nitrate leaching reduction. And eventually with this kind of tools, we can, combining with the satellite remote sensing, we can even run in the high resolution phases and located every single field to tell the farmers how they can get the benefit from the Kernza. And like what we have demonstrated at the end is like there are several maybe in the Minnesota we have several like very vulnerable drinking water areas, and for specifically for those areas alongside we might not suggest like very heavily planted plantations of the corn soybeans, and maybe we will recommend like have Kernza as an intermediate crop, so that can reduce the leaching, so that can improve the water quality. And we eventually we want to when we have this kind of robust model can extrapolate, we also going to package that as a kind of interfaces to general users, so that they can directly get the yield into the soil organic carbons for their specific field, and in maybe next year some estimations, so that they can decide whether they can have a Kernza being adopted in their field.
Very cool. I had one more question to follow up on the slide about data use and knowledge use.
Yep.
So we're taking data from glass box, process-based model,
Yep.
feeding it into KGML, but it says on that one of the features of KGML is mechanistic realism. And so it must not be the case that we just take the process-based data and stick it in a black box and it gives us the number. Because that would not have the realism. So how does that realism come through? You know, in X number of months when you're done, you've got these results.
Yeah.
And we try to interrogate them. How will we be able to do that?
Yeah, that's a really good question. I actually prepared one example. We have done that before. Like this publication is for corn soybean system estimations with KGML. What we are doing is actually we have using different kinds of ways incorporating the knowledge into the machine learning model to constrain the model extrapolations in space and time, so that in any given unseen scenarios, we have a constraint on that. The first constraint is we in the model structure itself, we add the knowledge, like we separating the plant soil variables, we considering the feedbacks from yield to the soil, and we let the model know the connections between these three variables, so that it will not only give you numbers, but it give you numbers with meanings. So that will be the first thing we do. It's not about the data, but about the scientific understandings directly incorporated into the model structure.
So rather than just saying like, here's a pilot that gives a prediction, you would say, you know, one of the things I want you to predict is the relationship between soil moisture and yield or something like that. And then, but it uses the pilot data to give you that.
Yeah, and so that is also that is not only can be achieved by architecture constraint, we have also other terms like this kind of different kinds of constraints. Like knowledge guided initialization is when we have those synthetic data, we can use the synthetic data to pre-train your model. So your model will already gain some knowledge how to map the moisture to the crop yield. And those things can like by doing that, we only need a little amount of the data in the real world to fine tune the relationships, not directly from the scratch of the mapping of how moisture influencing the crop yield. So that is a called knowledge guided initialization. Previously we used ecosys. In this project we use going to use epic model. And knowledge guided loss function is even more flexible and robust constraint during any kinds of scenarios. Like here, we can consider in the mass balance. Like we ensure that every predictions is within our expectation, and by not violating the mass balance, and how we did that, we add in the mass balance as another objective in the loss function, so that will punish the model whenever it makes the mistakes, so that it will not make any mistakes. And another thing is we also have some common knowledge constraints, like some thresholds we know but they don't know, like some data, they are emissions, they cannot be negative. We need to let the model know. So those thresholds can also be constraints. Whenever violating it, we punish the model. And also response control, meaning like moisture to crop yield, these responses, we can incorporating these empirical relationships into the model by adding those kind of a response curve directly into the model. And so that the model will try to follow the response curve, but also trying to follow the real world data, and so that it will not violating too much of the our expectations of this kind of response. So by adding those kind of loss functions, your model will not give predictions totally out of your expectation. And but in a more very complicated way, well, I cannot directly explain in a simple locations. But for example, response control, we totally use the 19 response controls for different variables to different kinds of input, the different target variables to different input. So those responses, like we can incorporate as many as you want.